Hello everyone, my name is Aurore Fass and I'm a third-year PhD student at CESPA, Germany. I'm very happy to be part of RuhrSec 2020, so welcome to my talk, HideNoSeek Camouflaging Malicious JavaScript in Benign ASTs. Let's get started with JavaScript. So initially, JavaScript was invented to create sophisticated and interactive web pages. However, as it offloads the work to the user's browser, it can also be used to engage in malicious activities such as drive-by-download attacks, redirections to websites hosting malicious software, or crypto mining. The question is, how can we know if a given JavaScript file is benign or malicious? Given the plethora of JavaScript files in the wild, we cannot obviously execute all of them to check for maliciousness. As a pre-filtering step, they can be statically analyzed to quickly discard samples likely to be benign, so that only samples likely to be malicious will be sent to more costly dynamic components. Several academic works have already been proposed to detect malicious JavaScript statically. For example, we have Kuyo, we have Zozo, we have JST, and all three of them combine an abstraction of the source code with machine learning algorithms to predict if a given file is benign or malicious based on what they have seen or learned before. Attack-wise, one system has already been proposed to break Zozo, but it tries to manipulate samples to specifically evade Zozo's detection. So here, with HideNoSeek, we go one step further and propose a generic attack to virtually bypass all of them. How do we do that? Well, we want to prevent the dynamic analysis of samples likely to be malicious. So the idea is to trick the detectors into classifying everything as benign. So HideNoSeek is our novel and generic camouflage attack against static JavaScript detection systems. Traditionally, benign and malicious JavaScript files tend to have a dissimilar syntactic structure. We represent their syntactic structure with the abstract syntax tree, so with the AST. And as benign and malicious JavaScript files tend to have a dissimilar AST, a syntactic detector, meaning a detector working directly at the AST level, can accurately distinguish them, of course. What we propose here with HideNoSeek is a system that automatically rewrites malicious JavaScript samples so that they have exactly the same AST, meaning exactly the same syntactic structure as existing benign scripts, while of course retaining the initial malicious semantics. And so by construction, our attack evades most of the static detectors. What's actually new with HideNoSeek? Well, contrary to mimicry attacks, which try to mimic benign structures by injecting benign features, we exactly reproduce an existing benign AST. So our attack is much more effective. Also, contrary to related works, which attacks one specific detector only and is tailored for it, our attack is by construction generic and can be applied to most static systems. For this reason, it works independently of any machine learning systems. Specifically, it does not need any knowledge of model internals or training dataset or classification scores as previous works did. Let's dive now into HideNoSeek. So HideNoSeek takes as input a benign file and a malicious seed, and outputs a new sample which has exactly the same AST as the original benign files, while retaining the malicious semantics. The general idea is to build an abstract code representation which enables to detect identical syntactic structures between the benign and the malicious inputs. We refer to these identical syntactic structures as clones. If we can find all the malicious clones in the benign sample, so all the malicious syntactic structures are in the benign sample, we can replace the benign clones by the malicious ones, meaning that we still have exactly the same AST as the original benign file, but we have now the malicious code. And finally, we do some adjustments so that the code will still run at the end. Let's focus first on building this abstract code representation. To do that, we will consider here the following JavaScript example. So we are defining two variables, x and y. Then we have an if condition, and if the condition is true, we're assigning the value y to d. We use the parser Esprima to build the AST, which you can see here on the slide. And as you can see, the AST provides a certain level of code abstraction. So specifically, it ignores the variable names and values to consider them as identifier and literals. For legibility reasons, I put the variable names and values on the slide, but it is important to notice that they are not part of the tree. So what you can see here is that the AST more or less is mapping each line of the code to a subtree, but we do not see any lines dependencies in the AST. For example, we do not see that D is defined only if the condition is true. Therefore, we now add some flow of control in our AST to be able to reason about the conditions. Specifically, we add two new control flow edges in the AST. So first, we have here, so we link here the non-predicate statement nodes with an epsilon dependency. And second, we link the predicate statement nodes with a Boolean, standing for the value the predicate has to evaluate to for this path in the graph to be chosen. Meaning that now, by looking at the AST, we can see that the block statement here, where D is defined, is actually executed only if the condition is true, which is exactly what we were aiming at. Great, but we cannot reason about the statement's execution order. So right now, we see three subtrees which seem independent of one another. Therefore, and finally, we add some data flow information to be able to reason about the statement's execution order. There is a data dependencies between two variables if the variable was defined or modified at the source node and used at the destination node. Meaning that X was defined line 1 and is used line 3, and Y was defined line 2 and is also used line 3. It also means that by following the data dependencies, we can see that 3 has to be executed after 2, and also that 3 has to be executed after 1. But we do not have any data dependencies between 1 and 2, meaning that they could be interchanged. So what we have here and what we built is an abstract syntax tree enhanced with control and data flow information. So with this code abstraction, we see now the semantic order of the code and not merely any arbitrary developing choices made by the programmer. Great, so let's go back to HideNoSeek. What we would like to do is the following. So we have here a benign JavaScript sample, and we have here a malicious seed. And we would like to rewrite the malicious sample so that it has exactly the same AST as the benign input at the end, while of course retaining its malicious semantics. And so to do that, we look for identical syntactic structures between the benign and the malicious inputs. And if we can find the complete malicious syntactic structures inside the benign files, then we will replace the benign clones by the malicious ones. And after that, we will adjust the remaining code so that it will still run at the end. So here specifically, we have 1 and A, which have exactly the same syntactic structure. You can see the structure represented on the slide. Also, 3 and B have exactly the same syntactic structure. So here we are defining a clone. We are defining a clone which is composed of two statements because the two statements are depending on one another. So you have the data dependency here in green. And you can note that for the benign clone, the clone is actually not contiguous because there is a statement 2 in between. So that's for the theory. And HideNoSeek can actually do that automatically and at the AST level. Great, let's do that. So let's first construct the AST. So as I explained previously, enhance with control and data flow information. So here on the slide, you can rather see an abstraction of the code with the data dependencies in green because obviously the AST did not fit on the slide, but HideNoSeek is working directly on the AST. So we do the same for the malicious sample. So here we are. And now HideNoSeek is comparing the AST of the two AST with one another, but here we are looking for identical syntactic structure, so between the benign and the malicious AST. So we are looking for clones. To do that, we will compare the syntactic structure of each benign statement with the syntactic structure of each malicious statement. So basically doing the cross product of all possibilities. Meaning that, we compare 1 and A, which actually already match. So that's great. We have found our first clone. And second, well, we would like to find non-contiguous clones. And to do that, we actually follow the data dependencies going backwards from the clone. So here we do not have any data dependencies going backwards from A, meaning that we continue to iterate. So we test 2 and A, which do not match, 3 and A, which do not match either. And so we continue to iterate, comparing the statements with one another, nothing is matching. Or here we have a match again. So 3 has the same syntactic structure as B. So we found a second clone, so a second entry, because this clone is not depending on the first one. And so as previously, we look for data dependencies going backwards. And so here we have one, so from B to A. And we will use them to look for non-contiguous clones. So now we will test 2 and A, which do not match, and 1 and A, which actually match. So we have found here a second clone in our current clone entry. Great. So now we do not have any data dependencies going backwards anymore, so we continue to iterate where we were previously. So finally, HideNoSeek could find 2 clones in this example here, and we retain only the second one because the second one is containing the first one. And if you remember the previous slides, it is exactly what we were expecting. So this one clone with the 2 statements inside, and the benign clone, which is non-contiguous. Also, you can notice that we find the complete syntactic structure of the malicious seed inside the benign sample, which is also exactly what we were aiming at. Great. So now we can begin to craft our malicious sample. At the beginning, our malicious sample is an exact copy of the benign script. But we could find the malicious AST inside the benign one. So now we'll focus on replacing the benign clones, meaning 1 and 3, with A and B. And when we have done that, we can focus on replacing the remaining code, meaning 2, 4, and 5, which has been impacted by our HideNoSeek attack. So first, let's focus on line 1. Here we have our benign code. We have our malicious code, which is a syntactic clone of the benign code, and here is our current crafted sample AST. And by construction, I mean, if you're still following me, the benign, the malicious, and the crafted sample, all 3 of them has exactly the same AST, which is represented here on the slide. So where is the difference between them? Well, it is in the names and values of the variable. You know, I mentioned at the beginning that these are not part of the graph, but are merely attribute of the leaves. So I just put them on the graph for legibility reasons. So here they are in orange and purple. So what I'm trying to say here is that replacing the benign clones by the malicious ones consists in replacing the benign attribute of the leaves by the malicious ones, because the remaining AST is exactly the same. So let's do it. Great, so here we are. And if we go back to the code, our crafted sample looks like that. So we do the same for 3, so replacing B in 3, and here we are again. The thing is, we have modified the benign or the crafted environment, which will of course result in the code not running anymore. Specifically, object is not defined anymore. So set attribute is not necessarily defined on I don't know what for an object anymore. The function create param is not necessarily defined anymore. So here we need some generic adjustments so that we still keep the same AST structure, of course, but that at the end our code should be running. So the question is, I guess, which nodes do we have to adjust? How can we know that? We can know that by recursively following the data dependencies here in green, originating from the replaced nodes, so that we can automatically adjust the nodes which depend on them, because if they depend on them, it means that they have been impacted by our replacement process. So let's take the example obj. So we follow the data dependencies originating from the replaced node. So here from W script. And by following the data dependencies, we get obj. And since there is a data dependencies between W script and obj, it means that we should just rename obj with W script, like that. And so here we do not have that problem anymore, that obj is not defined anymore. Great, so let's move on, set attribute. Well, this time it's a bit more complicated because, this is a method, it's not an object anymore. So now we need a method that can be called on every possible object with every possible parameter types and numbers, of course, without throwing errors or causing side effects. But it's actually not a problem, and JavaScript is even amazing here because we have several possibilities, so we can just take one randomly. So we took toString here. Great, and so now we have a similar process for a create param, except that we need a function that can be executed for every possible parameter types and numbers this time. But as before, it is absolutely not a problem, and we also have several possibilities, so we can randomly choose two so that we do not have the same one in the code, so decode URI and parse float. Great, so obviously we have been working at the AST level, so HideNoSeek is directly modifying the AST, meaning that at the end, we need to transform the modified AST back to code, and we do that with the ECMAScript code generator. And so here we have our generated code back. And as you can see, the crafted sample has by construction exactly the same AST as the original input used for the camouflage, while retaining the malicious semantics of the original seed. It is exactly what HideNoSeek is doing. Great, so how well does HideNoSeek actually perform in practice? To do that, we considered our data set consisting of over 120,000 different malicious files from 4 different sources. We clustered the file and deobfuscated and analyzed one sample per cluster until the initial malicious payload appeared. So at the end, we retain 23 unique malicious seeds, which are representative of our data set. And for example, we have droppers, we have different exploit kits families targeting different vulnerabilities, we have a crypto miner, and so on. As for the benign dataset, we extracted JavaScript from the Alexa top 10,000 websites, also including external scripts. In a second step, we downloaded the most popular libraries according to W3 tags. And so using these datasets, we can craft malware which have exactly the same AST as the benign samples while retaining the malicious semantics of the initial seeds. How many samples can we actually craft? So for our first experiments, let's consider only the high-profile web pages, meaning the Alexa websites as our benign dataset. In this case, and out of our 23 seeds, we could reproduce the behavior of 22 of them by generating over 90,000 samples which have exactly the same AST as samples from Alexa top 10,000 websites. Let's focus now more specifically on the seeds. We consider here the number of malicious samples we could craft per malicious seed, meaning how many benign AST can we actually reproduce with a given seed. For example, for MISC, we could reproduce the AST of almost 6,500 websites. Of course, the success of our attack highly depends on the syntactic structure the seeds contain and to what extent they can also be found in the benign scripts. For example, for MISC exploit kit and injected one, we could reproduce 78% of all the ASTs from Alexa top 10,000. On the contrary, it was more difficult for rig 1 dropper and rig 2, which contains some structures rarely present in the benign inputs. So overall, we could leverage 22 out of 23 seeds to produce over 90,000 malware, which have exactly the same ASTs as samples from Alexa top 10,000. Great. Let's focus now more specifically on the impact of our attack. So this time, how many seeds can we hide in a specific domain, meaning how many different malicious versions of a domain can we craft? We can reproduce the stored pages of Google and YouTube, meaning the 2 most visited websites 18 times, with 18 different seeds, which would of course maximize the impact in terms of infected users. It's pretty much similar for the other websites, except for Wikipedia. So here for Wikipedia, the start page did not contain a lot of JavaScript code, meaning that we did not have anything to analyze, so no clone to find, so nothing for HideNoSeek to work with. And similarly, for the libraries, we can reproduce jQuery version 1.12.4, which is used by 30% of the websites. So according to W3Text, we can reproduce a jQuery 17 times with 17 different seeds. Overall, for a given Alexa top 10 websites, we can produce on average 14 different malicious samples, which have exactly this one specific AST, and 13 for the most popular libraries. So our attack does have a high impact. Similar to Android in repackaged application, HideNoSeek documents could be presented as the original versions, so as the original websites or libraries for malicious purpose. And our attack would be especially hard to spot as we perfectly map an existing benign syntax. What about the feasibility of our attack in practice? I mean, how long does it take to generate such samples? So we measure the runtime of HideNoSeek on the two highest ranked Alexa pages, meaning YouTube and Google, in the two most popular libraries, Bootstrap and jQuery. As presented on the previous slide, we could craft 65 malicious samples, which exactly reproduce the AST of one of these two pages or of these two libraries. And it only took 16 minutes. So this is perfectly feasible in practice. As you can see here, the most time-consuming operation is the clone detection, so in yellow, as it is NP-complete. So here we were traversing the AST of the benign input of the malicious inputs, following the data dependency in the control flow backwards and comparing again. So this highly depends on the side of the AST, which we traverse repeatedly for the comparisons. Also, the code generation in dark blue and the AST, in particular, the data flow generation in gray, can take some time. So again, it really depends on the size of the tree that has to be traversed. So let's go back to our crafted samples. How do they look like? Well, by construction, of course, they have exactly the same AST as the original benign input, meaning that a detector working directly at the AST level would be foiled by our attack. We'll come back to that in a few minutes. Second, most of the tokens are common between the benign and the crafted scripts. Before explaining what a token is, let's have a look at these three JavaScript examples. So here we are defining three variables, x, y, and z, with different values. So an integer 0, a string 0, and the Boolean false. Still, these three JavaScript examples all have the same AST. And why? Because as I mentioned previously, in the AST, we do not have the names and values of the variables, but we just have identifier and literal nodes. Okay, so now back to the tokens. So the token is another abstraction of the source code where each word from the code is considered independently of one another and kind of mapped to a lexical entity such as keyword, identifier, punctuator, numeric, punctuator again. And so here we have three JavaScript examples. All of them have 5 tokens, but all of them have a token that is different. While numeric, string, and Boolean are represented by a literal entity in the AST, they are represented by 3 different tokens, meaning that our attack can change the tokens, but as I said previously, most of the tokens are common between the benign and the crafted scripts because only the literal token, if I may say, may change. So it means that we can also find JavaScript detectors relying on tokens and not just relying on the AST. But again, I'll come back to that in a few minutes. So back to the crafted samples. By construction, HideNoSeek modified the environment of the initially benign samples. Even though we did some automatic adjustments, we could not handle all possible cases. So we may have some crafted samples which may not run. And actually, 72% of the samples crafted with jQuery are still running. Finally, being able to run is not enough. We also have to ensure that the malicious part could be called or could at least be triggered. For example, if it is in a closure, we could not trigger it. And so here we have 65% of the running samples which do have a malicious behavior. So overall, we could craft over 90,000 samples, and roughly half of them, so 45,000, have a malicious behavior, while at the same time perfectly reproducing ASTs from Alexa top 10,000 websites. So finally, let's evaluate our camouflage attack in practice, so on real-world static detectors. Here is our pipeline. So we have our malicious seeds, we have our benign samples from Alexa, and we have our HideNoSeek system. We generated over 90,000 samples, and now we will classify these samples using different static detectors which we can find in the wild. Here we have two possibilities. Either the HideNoSeek samples are recognized as benign, which is awesome because it is a false negative, so it's showing that the attack is actually working, or the sample is recognized as malicious. If it is recognized as malicious, it's interesting because it has exactly the same AST as an existing benign input. So what is the classification of this benign input? So in this case, we also have a look at the benign sample which was used for the camouflage, and we classify it with the same detector. And here again, we have two possibilities. Either it's classified as malicious, which again is awesome because it is a false positive, so the attack is working kind of in the other direction, or it's recognized as benign. In this case, it's interesting because it means that the sample actually changed classification between the benign and the malicious version. Let's consider now the different static detectors we considered. So it's the three detectors I mentioned at the beginning of the talk. So we have JST, which is from us, and which is working directly at the AST level. And also JST is open source. Second, we have Zozo, which is also working at the AST level, but is also considering some information from nodes value. Zozo is from Microsoft Research and is not open source, so we re-implemented it for these experiments. As for Kuyo is working with tokens, so I presented what a token is previously. Kuyo is from Rick et al. And also not open source, so we re-implemented it for these experiments. All three JavaScript detectors are working with machine learning. So the first step consisted in training the detectors. And to do that, we considered our malicious training set from the wild, meaning that there is no HideNoSeek samples in the training set. We considered that HideNoSeek had never been seen before. And as you can see here, nearly all of HideNoSeek samples are misclassified, which is exactly what the attack was aiming at. So here, this is perfectly working. Let's see now if we can find a defense against our attack. So we leverage the fact that the machine learning-based detectors are able to learn. So we added some HideNoSeek samples inside the training set and retrained the detectors. This time, interestingly, the majority of HideNoSeek samples are correctly classified, so we do not have that much false negatives. So we decided to analyze the benign samples, which were used for the camouflage, and this time we have a lot of false positives. So why? Because the benign and the malicious samples have the same AST by construction, meaning that either all of them are recognized as malicious or all of them are recognized as benign. Still, for Zozo, we have 0.6% of the samples which change classification between the original benign inputs and the crafted samples. Why? Because Zozo is not only relying on the AST, but is also using some additional information in the form of variable values from the AST. And it's the same for Kuyo with 0.3 classification changes, again, because Kuyo is working with tokens. And as I said previously, tokens may vary between the benign and the crafted versions, but the majority of them are common, as we can see here with 0.3 classification changes only. So 0.6 and 0.3% classification changes, it's really negligible. So it's definitely too low to provide a useful and reliable defense mechanism against HideNoSeek. So overall, either the static detectors has never seen HideNoSeek samples before, and they misclassify nearly all of them, or they have been trained on such samples, and now they misclassify the benign input. So either way, you just cannot win. Let's think now about some potential ways to detect HideNoSeek crafted samples. So first, we could recognize the original benign document and see that the crafted sample is different from the original input it is supposed to be. In theory, yes. In practice, no. I mean, checksum tests would not be effective in that case because, for example, libraries can be altered for a benign purpose, like functionality extensions or caching proxies, or just stored together with other libraries. Next, you could argue that, well, HideNoSeek is adjusting the code it crafted. So we are using some calls to toString, for example. We are creating seemingly dead code as there is no proper usage of the result, which again is correct. So Defender could perhaps study the frequency of such artifacts. Correct again, but I would argue that the machine learning-based detectors we tested previously did not learn anything from that. And second, okay, let's say that the Defender is defining some very specific rules for such frequencies. It is likely to produce a lot of false positives. So based on our experience on JavaScript code in the wild, they are a lot of parameterless toString invocations. So seemingly useless calls are not a good indicator of HideNoSeek either. Third, well, HideNoSeek is an attack against static detection systems, so it does not necessarily also foil hybrid or dynamic detectors. That's correct, but dynamic detectors are slow, so they rather work on a pre-filtered list on samples likely to be malicious. And these lists tend to be generated by static systems, which are much faster. So HideNoSeek samples may not even be dynamically analyzed. Finally, what about a control flow and data flow based detector instead of purely syntactic detectors? Well, it is interesting and definitely not straightforward. So let's go back to our previous slide with the evaluation against the static detectors. To the best of our knowledge, there was no such control flow and data flow based detector when we implemented HideNoSeek. So for this reason, we implemented JSTAP. JSTAP is a JavaScript detection system which is composed of several modules, and each module has a different way of abstracting the JavaScript code statically. So here we focus specifically on the module, so AST++, meaning the AST enhanced with control and data flow information. And for the AST++ value, we're also including some additional information regarding variable names and value, similarly to Zozo. So JSTAP is also using machine learning and is also open source. With JSTAP, we perform the same experiments as before. And as before, we have a lot of false negatives when JSTAP was not trained on HideNoSeek samples. And we have, on the other hand, a lot of false positives when JSTAP was trained on HideNoSeek samples. We only have 0.2% classification changes between the benign and the crafted version. So definitely no way to recognize HideNoSeek samples. But why? I mean, HideNoSeek exactly reproduces the AST of benign inputs, while we have here some additional information in the form of control and data flow. That's true, but most of the control and data flow are common between the benign and the crafted scripts. Why? Because we're relying on control and data flow information to find clones. Because we're relying on control and data flow information to adjust the crafted code. So we have too few differences at the control and data flow level for JSTAP to be an effective defense in practice. So overall, the results did not change at all with the control and data flow based detectors. Either we have almost 100% false negative on HideNoSeek samples, or we have almost 89% false positives on the benign inputs used for the camouflage. So either way, neither AST nor token nor control and data flow based detectors were effective against HideNoSeek. To sum up, HideNoSeek is a generic camouflage attack against static JavaScript detectors, as it changes the constructs of malicious samples to perfectly reproduce an existing benign syntax. For this purpose, HideNoSeek rests on an abstract code representation to detect identical syntactic structures between the benign inputs and the malicious seeds. And then it replaces the benign clones by the malicious ones before adjusting the remaining code so that it will run at the end. In practice, we leverage 22 malicious seeds to craft over 90,000 malware, which have exactly the same AST as websites from Alexa Top 10,000. Also, our attack is highly effective in practice. When the static detectors have no knowledge about HideNoSeek whatsoever, they have over 99.98% false negatives on such crafted samples. And when they have been trained on HideNoSeek samples, now they have over 88.7% false positives on the benign input used for the camouflage. Meaning that the targeted lexical, syntactic, and even control and data flow-based detectors are inept to handle HideNoSeek samples, so they're not reliable in practice. HideNoSeek is part of a research project we conducted here at CISPA, so you can find more information in our CCS paper. Also, we decided to make HideNoSeek source code partially available, and on my GitHub account, you can find our abstract code representation, meaning the AST enhanced with control and data flow information, and also our clone detection module. For ethical reasons, obviously, we choose not to publish the actual attack, so the clone selection, the clone replacement, and the adjustments at the end. In addition, the different detectors we evaluated against HideNoSeek as well as our reimplementations are on my GitHub account. And with this, I would like to thank you very much for looking at this video. And if you have any questions or comments, do not hesitate to send me an email. Also, I hope to see you at RuhrSec 2021 in person. Take care.